Okay, lesson 3, understanding the derivative and linear approximations. We've talked. Do you guys feel like you've seen some of the same stuff between lesson 1 and lesson 2? You're still going to be seeing some of the same stuff. Yes, we're going to go a little farther with it, but we're still going to be seeing some of the same stuff. It's a matter at this point of trying to get all the connections made for you. Okay? So, there are times when we're interested in finding the effect of small change. And that's the idea of when we talk about the derivative, because it's a limit as h approaches 0, is a very small change there. For example, how's the revenue at your local theater affected by a small change in the ticket price for a movie? When you explore an application of the tangent line to a function called the linear approximation. Basically, it's the idea of using the equation of a tangent line, so using a line to approximate something. You've already seen that a curve lies very close to its tangent line near the point of tangency. So the closer you get to a tangent line, the closer that curve is, right? The farther you travel on that curve away from the tangent line, the farther off that approximation is. So if you zoom in repeatedly on the graph of f at a point, the function will appear to be linear. And actually, that's what this first example talks about. When you've zoomed in to a sufficiently small neighborhood around the point of tangency, it would be difficult to distinguish the function from its tangent line. This property of differentiable functions is commonly referred to as local linearity. So just the idea that we're going to take this sine function. If we zoom in on a certain section of sine, you zoom in enough, it looks like a line. Okay? So looking at example 1, it's an exploration example, so just kind of exploring some connections here. Use a graphing utility to graph y equals sine x. When they say graphing utility, you realize they're talking graphing calculator. Although I will say in Algebra 2 that doesn't have to have graphing calculators, Desmos is a graphing utility. I've really started introducing Desmos a lot with my Algebra 2 classes because this book really wants us to, do that. So graph y equals sine x. Now, with y equals sine x, what's the word I want to say? What mode do you have to be in for y equals sine x? Radians, yes. So physics kids, which is everybody, make sure you're in radians for this moment, please.
Yeah, I just tried.
And you don't get a sine curve if you're in degrees. So.
No. Yeah.
Okay, so right here it says put app. It has to be how you got in there. But we're going to exit whatever app you got into. We're going to go to number 2.
Okay.
There we go. Okay, so did you graph y equals sine x? And you got your traditional curve, yes? If you're in radians. Now, the idea here is, it says use the zoom in feature of the calculator at the origin 4 times.
4 times.
I think after about 2 or 3, it was looking like that second graph. It looks like a line. So just go to number 2, which is zoom in, and just remember you have to hit enter again. So the first time you basically get a sine curve. But then I think about the second time, it almost looks like a straight line. You can see a little bit of curve in there. So by the time you do this 4 times, it is a line,
Yay.
isn't it?
Yes.
And so that's where the idea here is we're zooming in at 0. So the tangent line when x equals 0 would basically look like this. If we knew the equation of that line and graphed it, they would be the same.
It is the same. When you just put in x, it's the same line.
Okay. Okay. So, okay, with that in mind, can you estimate the slope of this portion of the sine curve by inspection of this window? So whether it be on your graph, or whether it be, this is the version here in the notes, what would you say this slope is about? Does it look about 1 if you if you kind of look at the fact that right here, it's about up a half, and if you go about over a half, so let's rise and run the same. So it's not necessarily exactly 1, but we're just estimating here, right? Slope is about 1. what can you say about the slope of the tangent line at x equals 0 on the function y equals sine x? Well, what did we just talked about it, really. The slope of the tangent line is going to be 1 at this point, isn't it? Because we've zoomed in so much, we can see that. Now, I think she wrote it out in words. Do beware, guys. You need to be able to write words on, answers at times, right? And I'm not saying you always have to, but be able to write complete sentences. The slope of the tangent line at x equals 0 is 1, and I'm going to say on y equals sine x. So I wrote the slope of the tangent line at x equals 0 is 1 on y equals sine x, or on the curve y equals sine x. Ethan already said it, but what is it? What would be the equation of the tangent line? We just talked about there was a slope of 1. What's the ordered pair? There's a reason I didn't want to do that, but I'm off. Everything's off now. But the ordered pair would be, come on, 0, 0, yes, because on sine, when x equals 0, y equals 0. So what's the equation? If you think y equals 1 times x minus 0 plus 0, you end up with y equals 1x, right? And that's what your screen looks like, isn't it? Okay? Okay, so connection. The slope of the tangent line is the slope of the graph at that point. That's the connection to make. Okay, next page. Estimating derivatives of a function at a point. So here we are looking at sketching tangent lines. You might want a ruler. I will tell you this is going to be horrible on my behalf because drawing a line accurately on the BenQ, oof, it's very pretty in my notes. However, doing it accurately on here is a little rough. So you might want to grab a ruler. There's some rulers. If you want one, you may have one. There's some rulers in the little basket over by Maddie there. Yeah, I can't freehand.
You're gonna freehand?
You're gonna freehand?
I use a sticky note.
There you go.
That
Yeah.
was
And that's, you can always find a ruler someplace in your stuff,
This is
but
me telling myself what to do so I don't forget that.
I'm gonna bring this up a little bit so I have a little bit more room.
I should call the Homer Cott line at 6:59 p.m. See if they answer.
Have you ever called it?
No.
You're gonna be one of those
I wanna
people,
see-
huh?
I
Has
wanna see,
anyone
like-
ever called it?
No.
Have you?
I kind of want to see what it'd be like though.
But it's not open at 6:50.
I know, that's what I'm saying. See if they pick up. It's like a minute early.
Okay, so A, we want to use a straight edge to draw a tangent line beyond the point of tangency in each direction, and then it doesn't say it there, but we're just going to estimate the slope. So, unfortunately, I can't use a straight edge here, but on A, so when we're drawing this point, we're trying to draw it along there. I don't know. That's kind of the guesstimate of mine. And I'm going to say M sub A, as in the slope at point A, or the slope of the tangent line at point A. What are your thoughts? If A is a point, I don't know where else. It looks like maybe I went through right here or right here. You know, if I've just been doing rise over run. So if I rise 1, 2, 3, 4, up 5 over 1, or I could go up 6 over 1. You got the very top dot? Well, you know what? I got that too. So I would say the slope is around 5 or 6. Now, if you got the very top dot, are you talking about in that same line?
Mine was like 9/2.
Okay, well, 9/2 would be 4.5, which goes back to my 5 or 6. Very subjective here, yes? Meaning, are you in a ballpark? You shouldn't be giving me a negative slope. You shouldn't be giving me a slope less than 1, right? Okay, what about B? What do you know about B?
0 slope.
Yeah, that is at a max. They keep talking about this, right? At the max, the slope is always, the slope of the tangent line is always 0, yes? Okay. So at a max or min, your slope of the tangent line is always 0, and we're going to be making more connections there. Those are the ones I can draw on the BenQ. What about C? I have a hard time getting my line close enough. Ooh, there we go. That's a little bit better. I don't know. What'd you guys come up with?
I have -2.
I put -2.
Yeah, I could go with -2. Are we in the ballpark if you're not right there? You know, -1, -3. I know there's technically a big difference, but... And what I told someone this morning during homeroom, you're not going to be drawing tangent lines and trying to find the slope of them on the AP test. Okay? That is not the focus of this skill here. So if you're stressing about I can't ever get the same slope as Mrs. Sargent, don't stress.
I want
Okay?
that to be on the test.
It's
It's
fun.
easy.
I don't know. It would be stressful to me. Okay. So moving on. Let's see. A. What happens when we draw the slope of the tangent line here? It's the same as that line, isn't it? Okay. So the slope of A, or the slope at A, is going to be whatever the slope on that side of the graph is, yes? Now, this is one where, let's see, is A directly on a point? Yeah, I guess A is directly on a point, isn't it? That's the other thing. Some of these she does not put directly on a point, and that makes it really hard to find the slope, doesn't it? So, I have a slope of, I about messed up, not 2, but -2. We'll come back and talk about B here in the end. What about the slope at C? It's going to be a +2, I believe. Now, the slope at B. I need you to realize that the slope at B here is a different situation than the slope at B in the previous graph. Okay? We have a different situation occurring. Over here in this previous graph, this was the max, and it was a max on a curve. Okay, so when you draw a tangent line, you can draw a tangent line at that curve. Okay, and the curve is kind of supporting it. Over here, it's a minimum, but this point is what I would call a hard point or a sharp point. And that situation is different. Okay? We can't draw a tangent line there because a tangent line is just going to kind of be teetering out in the middle of nowhere. It's not like here it rests against a curve. It's not resting against a curve, it's just kind of teetering out there. You could also think about it in terms of limits. The limit from the left as we approach the limit from the left is negative 2. The limit from the right, as you approach the limit from the right, is 2. Okay, in terms of as you're following that line. Okay, I shouldn't use the word limit there, sorry. But so the slope at B does not exist. Okay, a hard or sharp point, that slope does not exist. And so if you want a little bit of vocabulary, I have written down in my notes that this is a sharp point. It's just that it's not part of the curve. It's a sharp or hard point. And that does mean something different in calculus. Okay, C, you ready to talk about C? And I don't know how precise we have to be with all of this because I don't want to spend, we can get really bogged down here, I realized. Slope of A. See, this is where I struggle, where A is not at an intersection, is it? And so it makes it a little bit harder to find a slope when you don't have, it's not at an intersection point. But
Can we just say something?
you can try it. I mean, what I kind of do in my head is I kind of think, okay, if I move up a little bit there, where's another dot that could move up a little bit? What did I have here?
Negative a third.
Okay. Well, based on what I have drawn up here, I would agree with negative 1/3. I'll be honest, my answer key says negative 1/2. Huh? Okay, so ballpark here, right? Negative 1/2, negative 1/3. Are you getting something along those lines? Should be negative, should be a fraction. I'll put 1/2 because that's what I have in my notes, but I'm not going to argue negative 1/3 either. It's very subjective here. Let's go ahead and do C and we'll come back to B again. Okay. What about the slope at C? So for me, this one is closer to 1/2.
I'd say that one for me was 1/2.
Yeah. I have, in my notes, I have negative 1/2 and 1/2 as the two different slopes here. So, again. What do you think I'm going to say about B? Okay, the slope of B does not exist. The vocabulary I'm going to use here is that B is what they call a cusp. Okay, vocabulary point B is a cusp. And the difference, why it's called a cusp as opposed to a hard point, I mean, it's also a hard point, I see that as well, but the curves coming into it, it's not straight lines coming into it, but the curves coming into it, it can be called a cusp. Okay? Okay, D. What are you thinking here? How are you going to draw the tangent line at A? Straight vertical? I mean, you've got a positive slope going into it, a positive slope going out of it, but at A, it is a straight vertical. Not that I can draw straight vertical, but it is. And so what does that make the slope? What's the slope of a vertical line? Undefined, does not exist. 0 is a horizontal line. Because 0, when you do rise over run, that's rising 0, running however many, so 0 is for a horizontal line. On a vertical line, your rise is infinite, but then your run is 0. So any number divided by 0. Sorry, I'm watching Connor's face back there. You see why I said I don't know how I can get through this in 2 days. It is. And I really can't afford to take a third day, so we're just going to keep plugging. Speaking of, moving along. Example 3. The position of the tangent line relative to the function it models depends on the concavity of the function at the point of tangency. That's a lot of words, right? What? Okay, I'll explain here in a moment. Throughout the course, you'll be required to explain, justify, defend your knowledge using proper terminology and precision. Use the graphs from example 2 to complete the following statements. Okay, when a curve is concave up, do we even have anything being concave up? We didn't have anything concave up, really, do we? Huh? Yes, you could. Or we could look here if you want. Like if I drew... Okay, first of all, concave up, concave down. We haven't talked much about concavity, right? Do we know what concave up versus concave down is? I'm trying to remember if we talked about it in pre-calc or not.
Talked a little bit back.
Okay.
I think is one of them like convex then?
So, and I don't know where, find a spot to put this in your notes, I guess. Concave up is when something is bowled upwards. Okay, so for instance, as Connor said, a parabola. That's concave up. Okay, something that is bowled up. An exponential function, a regular exponential function, that could be considered concave up. Does that make sense? As opposed to what's concave down. So concave down is, instead of a parabola opening upwards, it's a parabola opening downwards. So it's bowled downwards. You could take that exponential function, and that could be considered concave down. Anything where the curve is going down. Something like a sine curve switches. It's concave up, concave down. Concave up, concave down. Does that make sense? Okay. Now, with this in mind, when the curve is concave up, where is a tangent line going to be on that? It's going to be somewhere outside of the curve, yes. Or in this case, specifically below the curve is what I want to talk about. So when the curve is concave up, the tangent line lies below the curve. Okay, obviously at the point of tangency, they're the same. But the connection I'm trying to get you to make is the tangent line then has a little bit smaller value than the curve because it lies below the curve. Now, when the curve is concave down, so concave down, where's the tangent line? Your tangent line is going to be above the curve. Okay. At a turning point or a max min, the tangent is blank or blank. Well, what is the tangent at a max or a min? 0. A turning point. So right here in D, this is a good example. This graph turns. Right here, do you see on the bottom part, it's concave up. And then what happens? It goes through this point, and now it is concave down. So what is the tangent line here at the turning point or point of inflection? That is a vertical, right? Oh, wait a minute. I'm combining things. Okay, hold on. I'm combining things. I was misreading what they mean by turning point. Okay. Turning point / max min. That is a slope of 0, or in other words, the tangent is a horizontal line. Sorry. I was misinterpreting what I was supposed to be saying there. So I looked ahead at the next one. I was like, wait a minute. Because then D says, at a point of inflection, the concavity changes. So this is a turning point here as a max or min. Over here, this is the point of inflection. Okay, this is an example of a point of inflection because my graph goes from being concave up to concave down. And that tangent is what? It's a vertical line, isn't it? So that tangent is vertical. You know what? Depending on how you drew that, so if we look at that one there, that would be a horizontal. But if we put it right there, nope, that one wouldn't work. Never mind. Okay. So yeah, vertical. At a sharp corner or cusp, what did we say about the tangent? Does not exist. And at the point on a linear function, the tangent is, so we didn't have a linear, but we had a v up here, yes? Each piece was linear. What was the slope of the tangent line? It was the same as slope of the line. Okay, so at a point on a linear function, the tangent is the same slope as the line. However you want to write that. Same slope as the line. Okay.
I have a question.
Yes.
Why didn't we just draw on D? Why didn't we just draw horizontal?
On D,
Yeah.
why didn't we just draw it horizontal? Because it wouldn't, if it's tangent, it has to be, that would be cutting through it as opposed to running alongside of it, if that makes sense. And we need to kind of go alongside the curve. Okay, I'm going to have to write small here because too many pages in the notes today. I did not have room to blow up all my pages. Okay, consider the radical function y equals the square root of x. A, use the difference quotient to find the slope of the curve at x equals 9. What are we basically using? They want us to find slope. They're saying use the difference quotient. This is basically what? Definition of derivative, right? Derivative finds slopes. Derivative finds slope. And then the difference quotient is what makes up the definition. And so I'm going to use the limit as h approaches 0 of f of x plus h minus f of x all over h. So if I do that here, the limit as h approaches 0, we're using square root of x. What is f of x plus h? Take the x, replace with x plus h, it's square root of x plus h, minus f of x is square root of x, all over h. When you see those two radicals being subtracted, what do you know you must do? We're going to have to multiply, right? We're multiplying by the conjugate of, in this case, the numerator. So on top, since it's square root of x plus h minus square root of x, we're going to multiply by square root of x plus h plus square root of x. Equals the limit as h approaches 0. What happens in my numerator when I FOIL that? Square root times square root gives me x plus h. My outsides and insides will cancel. Then negative square root of x times positive square root of x is going to be minus x. All over h times square root of x plus h plus square root of x. Notice in the numerator, x minus x will cancel. The limit as h approaches 0 of h over h times square root of x plus h plus square root of x. What can happen here? H on top and h on bottom can cancel. So the limit as h approaches 0 of 1 over the square root of x plus h plus square root of x. You may have omitted some steps or whatever. I know you guys can fit it in a lot better there. See, mine fits perfectly fine on paper, just not on the screen. How do I find the limit as h approaches 0? Direct substitution. 0 in for h, yes? And when I do that, I'm going to have 1 over square root of x plus square root of x. What is square root of x plus square root of x? 2. 1 over 2 square root of x. So we just found that f prime of x is 1 over 2 square root of x. I feel like you did this last night in homework, actually. Because I talked to somebody about what plugging the 0 in and what it worked out as. Okay, we should have saved ourselves some time. Now, what did the question ask us for? Slope of the curve at x equals 9. So what am I finding here? F prime of 9. So 1 over 2 times the square root of 9. What is the square root of 9? 3. And so we end up with 1 over 2 times 3, 1/6. Okay. Part B. Unless you guys have, was A okay? Let's review, yes? Good. It's good practice. Okay, B. Write the equation for the linear approximation of f near x equals 9. Well, what do we need to write? An equation for linear approximation. What am I asking you to write? Equation of the line, right? Equation of the tangent line. It says equation for linear approximation. That's their fancy way of saying equation of the tangent line. In order to write the equation of the tangent line, we need two things. We need point and a slope. Well, we already got the slope, yes? Slope was 1/6. What's my point? 9.3. Because x was the given as 9. And then if you put 9 into the original function, the square root of 9 is 3. So can you write that equation? Maybe you already did. Y equals 1/6 times x minus 9 plus 3. Now, for part C, it says use the equation in B that we just wrote to estimate the value for square root of 9.1. Do not use a calculator. Believe me, it's possible. I know, you guys don't want to hear that, but it is possible, and it's not as horrible as you think. So we're finding, what are we doing? F of square root, no, wait. We're trying to find the value of square root of 9.1. We're trying to plug 9.1 into that equation, right? And so when we do that, it's going to be 1/6 times 9.1 minus 9 plus 3. Well, okay. 1/6 is 1/6. What's 9.1 minus 9? What? 0.1? It's 0.1, which is 1 what? 10th. So what if I say that this is 1/6 times 1/10 plus 3? 1/6 times 1/10 is 1/60th, plus 3 makes it 3 and 1/60th. Now, I will say I did not figure that part out by hand. I used the calculator for that part. And I had to laugh, though, because when I was checking, I don't always listen to all of her videos, but I check certain things. And when I was checking her video, she was talking about putting it into the calculator. I'm like, it says don't use a calculator. So 3.0166, is that what it is? I think, and it goes on past that. I think the 6 is repeating. Yes, no? I feel like it is, but I'm not 100%. No? Okay, so it's not a repeating decimal. For some reason I was thinking it was a repeating decimal, but, so. Okay. Well, okay. So 0.01666 and then a 7, that's the calculator rounding. So yeah, it is a repeating decimal there. Okay, so we've got that answer. D, graph the function and its tangent line at x equals 9. Okay, the function. Do you guys remember from pre-calc what square root of x looks like? Think 0, 0, 1 comma what? 1, 1. What's the next value I should put in? I don't want to take the square root of 2.
4. Just kidding.
Square root of 4 is 2. Then the next value? Square root of 9 is 3. Square root of 16? 4. That's what she set up. That's what the graph is set up for. Remember, y equals the square root of x is half of a sideways parabola, yes? It's half of a sideways parabola. Now, the tangent line, like I can do this, at x equals 9. So that's this point right here, and that is attempting to draw the tangent line. So the tangent line being something along there, yes? Okay. So E, explain whether your answer to C, so this right here, is an overestimate or underestimate for the actual value of square root of 9.1. Justify your answer by reference to the behavior of the graph. This is what we just talked about on the previous page. Where is my tangent line in reference to the curve? It's above. So what is my estimate going to be? It's going to be an overestimate because any value on that tangent line is just slightly too big. Does that make sense? Or maybe a lot too big, depending on where you're at. I mean, obviously, anything close to 9, you're going to be close, but not exactly. So, now, think about this curve. What if I say this curve is concave down, yes? So that goes back to the other page as well, is that my curve is concave down, So it is an over approximation because the tangent line lies above the curve. So I'm going to say an overestimate. I would love to get more formal, but I'm running out of time. I'm going to say overestimate because tangent line is above the curve. Now, gosh, that was sloppy. F. You plug in square root of 9.1 in the calculator. It's 3.01662, and then it goes on from there. It's not repeating, but something. Does that make sense that it was an overestimate? 3.0166666 is a little bit bigger than 3.0166662. Yes? So we're close. Now, we were close because 9 is right here. And where's 9.1? Right next to it. Yes? So we're very close. Would it be accurate for the square root of 25? So if I go out here to 25, is my tangent line going to give me an accurate estimate? No, this tangent line is accurate where? In the small neighborhood of 9. Is it going to be accurate way far away from 9? No. And so square root of 25 is too far away from the point of tangency. It's outside the local neighborhood. So square root of 25 is too far from point of tangency, which was x equals 9. Okay? Are we okay with the end? I pushed a little bit at the end, I know, because I saw the end of the period coming. Okay, guys. We only have 5 sides to do tomorrow.
Maybe she has longer class periods.
Or